Science Lines. Hello. I'm so sorry if you're watching live that I was so late on. It wasn't a family emergency. It was me getting very distracted by a child, and then by the end of the distraction, completely believing that it was Thursday and it's Wednesday. Let's learn about refraction. Hello, I'm Lara from Theatre of Science. This is the IGCSE module, and we're learning about refraction. It's almost a self-contained lesson, really. It's actually lesson 4 of the waves lesson. But I love this one because it very much does just kind of stand alone. It starts with a really obvious activity, but one that kind of blows my mind every time. Have you got a glass of water and a tablespoon? Or a pen, just some sort of stick-shaped thing? Can you just, first of all, put the pen or the tablespoon, the stick type thing, into the middle of the glass of water and tell me what you observe? It actually gets a little bit bigger, but that's not what we're talking about today. If you watch my all ages theme park lessons, we just did a lesson on aquariums where we talked about why it gets bigger. We will talk about that in a few weeks' time. But hopefully, apart from it getting slightly big, you haven't really noticed anything. Move it side to side. Oh, gasp. It's like it's been completely cut in half. What is that? How is that? I mean, I know that we just sort of accept it, don't we? But when you think about it, that's totally amazing. It really looks like one end of the spoon has been completely broken off from the other end of the spoon. How is that happening? So what is happening is refraction, which you might have guessed because this whole lesson is about refraction. What is actually happening is, so we have talked about how light travels at 300 million meters per second. That is true, but it travels at 300 million meters per second, the fastest that anything in the universe can travel, as far as we know, in a vacuum where there are 0 particles. But it slows down when it hits different medium. Medium is the posh word for kind of stuff. So light slows down when it travels through Earth's atmosphere. Air, it slows down when it travels through glass or water. And when it slows down different sort of parts of the light slow down in different ways. And it seems to bend. To explain why this is possible, I need my bit of turf to pretend to be some, well, it is some grass, and a bit of black paper to pretend to be a road. This is a beautiful model. I did not make it up. I learned about this in my physics lessons, and it's a delight to pass it on to you. It just really helps with the understanding. I've got this Lego tractor here. And I want you to imagine that the Lego tractor is travelling along a road, just a tarmac road, very smooth road, very easy for the tractor to travel along the road. And then it's going to hit some rough grass. Tractor probably not a perfect thing to use because tractor's obviously kind of designed to go on rough surfaces, but for our purposes, let's say it's very difficult for this tractor to travel on the grass, okay? So it travels along the road, easy peasy, nice and smooth, not very much friction. What's going to happen if the grass is at an angle across here? Well, the wheel at the top is going to get stuck, right? It's going to slow down, not get stuck, but slow down. And this wheel at the bottom is going to carry on moving at the same speed as it was before. So what's going to happen? What's going to happen in that case? Well, it's as if you were walking along, say you were like swishing through water up to your knees, and then that water turned into treacle. The foot that was stuck in treacle would slow down, almost come to a stop. The other foot would carry on, and you would turn, right? So can you see that tractor is going to turn? That wheel's got stuck on the grass, or is slowed down because of the grass. That wheel's going faster, so it's going to pivot like that. Is that all right? If you can understand that, you've pretty much understood refraction, because the same thing happens with light. If you imagine that the tractor is a light wave and that the road is air and that the grass is, say, water or glass, then when light hits it at an angle, it slows down one side more than the other and it bends. Another example for you is a square fish, an unusually square fish hitting some water. So let's say that the fish is traveling through the air. It's got this very flat face. It's getting to some water at an angle. The little corner that I've marked here with a star, the bottom left corner, is going to hit the water first. So the fish is going to slow down and change direction, as shown. So the boundary line, which you might hear talked about, that's just the line between the medium, so between the air and the water in this case. Okay, so here's a diagram showing you what actually happens in that activity that we just did. So this is the spoon, say, or the pen that was in your water. What's happening is that light is shining from the pen or the spoon or whatever. It's hitting the glass at an angle. This side, let's say the cap of the pen. This is what I'm always doing, by the way. Even if I was in an IGCSE physics exam, I would be getting my pen out just to double check. In this case, the lid of the pen is escaping the glass of water first, if you like. So this side's going to speed up. This side's still in the water, right? So it's going to be going slower. So it bends that way. What your brain does is your brain knows that light travels in straight lines. It knows this. So it sees light travelling from this direction, carrying the information of the pen or the spoon, and it thinks, okay, the spoon must be over there. And it sort of makes up this image somewhere where it's not. Is that okay? So where the pen is above the water and the light is just travelling through the air, you don't get that bendy effect and you see the spoon where it actually is. But where light is travelling through the water, the spoon appears to be in a different place. It's good, isn't it? And it doesn't happen when you completely centre it, because the light isn't hitting the glass at an angle, so it's just coming straight through like that. You wouldn't get any refraction. So refraction is basically just light bending because it's travelling across mediums, from one medium to another. Is that all right? I've heard a message. I'm sorry, I was so late. I just raced back into my office and panicked and threw the screen on. Yeah, you haven't got any comments on, have you? I thought I'd left comments on this video, and I haven't had time to put up a Facebook post. If you're wanting to comment live, then on my Facebook page, certainly by the end. Can you write down your question for now? And I'll put a post on my Facebook page so that you can comment at the end. Have a go at this for me. It sort of, hopefully it starts off quite easy, and then it works up to questions that you might actually get at IGCSE. I've got a few different situations here, and I want to tell you to tell me, will the thing speed up or slow down, and which direction will it go in, and can you draw a line? So, number one, a weirdly square fish leaping out of water, if it's going from water into air, from the bottom left of the screen, and it's going towards the top right, is that fish going to speed up or slow down? And which direction is it going to... It's going to change direction, but which direction is it going to change direction towards? Number two, Wormy, Theatre of Science mascot Wormy, rolling to the shoe shop. So she's more or less in a straight line. Her head's at the right, her tail's at the left. There's some mud running from the bottom left of the screen up to the top right of the screen. She's about to hit the mud with her head. Is she going to speed up or slow down? What direction is she going to go in? A steamroller, it could happen, hitting a triangle of glue. What direction is that steamroller going to go in? Question number 5, starting to get a little bit more sensible now. Light moving from air into glass at an angle. So coming from the top right towards the bottom left where the glass is. Speed up or slow down, what direction is it going to bend in? Same question again, but this time light is coming from the top left towards the bottom right, and this glass block again, it's going through the glass block actually, and it's coming out into air. Number 7, light moving from air to glass. So this time the light ray is going from the top left through the air and then hitting the glass, which is in the bottom right at horizontal. Which way is that going to bend? And if you've done that all, can you show how light travels through the glass now at the other side? So number 7, you've got a light ray going from air into glass. Can you tell me which direction it'll go in? But then, yeah, can you also say, when that light ray comes back out of the glass, what's going to happen? Have you had a go? I'll give you like a couple of more seconds. Okay, let's start going through the answer then. This weirdly square fish leaping out of the water, well, it's coming out of the water. I'm just going to pretend that my pen is it, and I'm going to do this every single time with no apologies. So my pen comes out of the water, the top of my pen hits the air first, so that's going to speed up. The bottom of my pen is still in the water, so that's still moving quite slowly. So it's going to bend towards the right. Is that okay? And it's going from water to air, so it's going to speed up. Luckily, light behaves quite similarly to us in that sense. There we go. So it's going to do something that looks a bit like that. Wormy rolling to the shoe shop. Well, her head's going to hit the mud first, so she's going to slow down. And if her head's hitting the mud, I find it helpful to imagine that it's just got stuck in the mud. But if that end of her was still moving, and she would end up bending off to the right as well, and she would slow down. There we go. So I could draw a line like that. Steamroller hitting a triangle of glue, it could happen. So as we're facing it, the left of the steamroller is going to hit the triangle of glue first. So if you imagine that bit gets stuck, it's then going to turn and move towards the left, isn't it? And it's hitting glue, so it's going to slow down. Light moving from air into glass, it's moving into glass, so it's going to slow down. The bottom, if you like, of the wave is going to slow down first. So if that bit's moving slowly and the top bit's still moving quickly, it's going to bend sort of towards the glass like that. Light moving from glass to air, what's going to happen there? So again, the bottom of the ray is going to hit the air first. So the bottom of the ray is going to speed up, whereas the top bit of the ray in this diagram is kind of still stuck moving slowly through the glass. So again, it's going to bend off towards the right, isn't it? Terrible with left and right. And now this one, it's going from air to glass. So the bottom of my pen is hitting the glass first. That's going to be the bit that slows down. So it's bending, well, it's bending towards the left, I suppose you would say. And it's going to slow down when it hits glass, speed up if it goes from glass to air, and slow down when it goes from air to glass. Phew! Okay, do you remember last week? So last week we looked at reflection and how things see reflections in mirrors. We talked about the very important point, which loads of people forget when they're panicking in an exam. You can only see things when light travels from the thing into your eyes, okay? So in this weird close-up diagram, someone's seeing the reflection of it's the bottom of a rubber duck actually, in a mirror. That's the person's eye. That's the rubber duck, which is really in the room, so light has to be travelling from the duck and bounce off the mirror and into their eye for them to be able to see the reflection of the duck. And I asked you to label some different things, which hopefully you didn't have too much of a problem with, because you can do it by process of elimination. You've got the ray of light coming onto the mirror, the ray of light being reflected off the mirror, and then you've got some different angles. So we said, hopefully it's fairly easy to work out that the ray of light bouncing off the mirror is the reflected ray. So therefore the incident ray is going to be the ray shining onto the mirror, and it is, or the ray shining off the object, the incident ray. So last week we said, okay, the angle of incidence then is the angle between the normal and the incident ray. The normal, you remember the normal is this dotted line that we're drawing at right angles to the mirror. And it's there to show the angle of incidence. So the angle between the normal and the incident ray, angle of incidence, and the angle between the normal and the reflected ray, angle of refraction. All right? I didn't have too many problems with that, did we? Well, have a look at this. So this time we've still got a normal. Instead of a mirror, it's a block of glass. So you've got air, block of glass, a normal going at right angles to the boundary between the air and the glass, and you've got a ray of light shining through the air and then slightly changing direction as it goes into the glass. Could you label for me which one the incident ray is, which one the refracted ray is, which one the angle of incidence is, and which one the angle of refraction is? What do you reckon? And if you've done that, if that's toots easy, what direction is the light going to go in when it comes out of the glass? So imagine that this ray of light continues through the glass in a straight line, because it hasn't got any reason to not travel in a straight line, has it? Until it gets to the air, because that's a change of medium, so it's going to change speed. Which direction is it going to go in? It's up to you. You might have the worksheet from my website, in which case you can scribble on the worksheet, or you might be sketching on paper, that's fine too. You've got to be so careful with your angles, haven't you? Remember, what is the normal there for? Like, what's the point of the normal? Why would we even draw a normal on? I'm going to give you a second or two, because I think it'd be useful for you to start thinking about the last question, what direction the light is going to go in when it comes out of the glass. See if you think about angles. All right, well, hopefully you were all right with the incident ray being the ray that is shining inwards, like towards the glass from the object. So the refracted ray is going to be the one that has changed direction, right? It's changed direction because the ray has hit the glass. So the angle of incidence is the angle between the normal and the incident ray. Be really careful, it's so easy to get confused and think that it's between the glass and the incident ray. But what is the normal there for? And the angle of refraction is between the normal and the refracted ray. Where's that light going to go? Well, it's going to continue, and then what's going to happen? Just get your pen out. We're traveling along, we're traveling along, we're traveling along. What's going to happen? Okay, so it's the pen, the top of the pen, isn't it? The bit I'm holding, which is going to come out into the air first. So that part is going to speed up. So if that bit's speeding up, it's going to bend downwards again. And it does. If we draw a normal, partly to show the examiner that we know what we're talking about, and partly so we can get the angles right. Look, gasp. Oh, someone was saying on Facebook yesterday, oh, interesting that the angles aren't the same like they were in reflection. No, but look at this. So that angle and that angle is the same, which is quite interesting, isn't it? So that's the angle of incidence, and that's the angle of refraction on either side of the glass block, and they are the same. Right, let's do the bowl trick. Some of you will have seen this before. It's such a good trick. So if you've got a bowl of water and a coin, pardon me, an empty bowl to start with, and a coin, and like a large glass or a jug of water would be ideal. Can you put a coin in a bowl and then step away so you just can't see the coin? I'm going to prop you up on this little box with some Lego so that you know I haven't cheated. Here we go. Make it a little bit higher, I think. So you need to just move back just enough. Prop you up on this little Lego person so that you can't see the coin. Only you need to just not be able to see the coin. So there's the coin, okay? I'm going to push it. There. Can't see the coin, can we? And I'm definitely not moving the camera. And now you just pour the water in. You're going to have to trust me that the coin does not move. Gasp! What's happening? You should find, and I'm so sorry, I should have asked you to predict what you thought was going to happen. The coin comes into view! Wow! That's good, isn't it? Come on, that's good. Now I'm going to do the most brutal thing I think I've ever done on Theatre of Science. Horrible, horrible thing. That was a really lovely fun trick. Can you sketch a diagram to explain how the bowl trick works? Now, probably the answer is no. I've taught this lesson several times now, and the answer for me, to be honest, still kind of no. But I want us to do it anyway, because if I just show you a diagram showing how that works, we're not going to have learned anything. We need to feel uncomfortable. It's really important for our learning that we feel uncomfortable, to fuse some neurons together, so that when we see the diagram of how it works, we're invested and we understand it better. Okay? So I'm doing it with you. I'm doing it behind you. Sketch a diagram to explain how the bowl trick works. So what happened? There was a bowl with a coin in it and just air, and light travelled from the coin, but the bowl was in the way, so the light couldn't get into our eyes. Yeah? And then we filled the bowl with water, and magically, not magically, the coin came into view. So when the bowl was filled with water, light was somehow able to get from the coin into our eyes. Just have a play, all right? Have a play. I'm expecting, nay, hoping, you to do lots of scribbling out and dashed lines and real lines, and yeah, try and work this out, and I will I will do the same. I didn't do a fabulous job of it yesterday, but it doesn't matter. It's about learning. All these notes are probably going in the bin or getting washed off afterwards. Okay. I literally only taught this yesterday. Right. Okay. You might want to draw, she says it occurring to her as she does it, you might want to draw more than one diagram showing that before and after. Like I've done this, right? This is the first thing that I've done. I haven't really thought it through. I've drawn an eye, I've drawn the coin, I've drawn light travelling from the coin to the eye, but I've drawn the bowl wall in the way. That's right, isn't it? That's what was happening first of all. Light couldn't get from the coin to me because the bowl was in the way. That's right. So now I need to draw a line to show that there's water in the bowl, and I need to think about how light moves after that. Is that all right? You do you. I'm not saying that that's correct. I'm just trying to explain my thinking. Easier for me as well, of course, because I've got a whiteboard, so I can just rub little bits off whenever I like. You probably have to like, scribble out or rub out, whatever. Okay, right. I've got what I did yesterday on the board, and then I know where I've gone wrong because I did it yesterday. So I've drawn that now, okay? First of all, I drew a line just going straight into the eye, and then I knew that wasn't right, so I filled the glass with water, but that was good because at least it meant the coin was in the right place compared to my eye. And then I filled this with water, and I thought, okay, so light has gone from the coin and then it's bent towards my eye. And then I checked with my pen that was what was going to happen. So if a light ray was coming off the coin towards the water, that lid of the pen there would hit the air first, wouldn't it? So that bit would have sped up so that it would have bent in the right direction. I'm going to draw an arrow on because I'm just going to get used to doing that for IGCSE to show light going into the eye. Cool. So I can rub that out. That's what I did yesterday, having not taught this lesson for a couple of years. But that's not quite right, is it? It's not quite right, is it? Well, maybe it is, but my brain knows that light travels in straight lines, doesn't it? My brain knows that light travels in straight lines. So my brain, if I wanted to show how I saw the image of the coin, how the coin came into view, is that what happened? My brain's doing something extra, isn't it? my brain is getting information of the coin from that direction, and it's going, oh, okay, cool. Light travels in straight lines, so the coin must be somewhere along this line. We need a dotted line, because that's the image that my brain's kind of making up. So the actual coin, the image of the coin is over there. I had to make my coin small to fit it all on. Phew! Do you know what? Wow, I think it only took teaching that lesson like 10 times. Oh yeah, I really wanted you to do lots of crossing out. This is just a thinking exercise. That's the image that I found online that I liked. But I think it's probably taken 10 lessons of teaching that for me to be able to actually draw that out by myself. It's a nice position to get to. It shows you've revised enough if you can do that. Teaching is definitely the best way to learn anything. Right, shall we move on? Because scientists, they're just amazing. And I don't mean scientists really, I just mean sort of curious humans throughout life. It's not very useful if you're going to do like science or engineering, if you're a physicist. There's very few things that it's useful to talk about if you can't put numbers on it. You can't just say, oh, light slows down when it hits different medium. How much does it slow down? It's important, isn't it? If you're going to build things and invent things, you need to know exactly how much light slows down when it hits, for example, glass compared to water, compared to vegetable oil, more of that at the end. And we can measure how much a material slows down light or changes the speed of light. And it's called its refractive index. And the symbol for refractive index is a little n. So you're all at different levels with your maths. Some of you will be really comfortable with trigonometry and some of you won't be. So I'm not actually going to give you any example questions here. I'll set you some homework. But here's the equation, that how much a material slows light down. You can find it out by doing the speed of light in a vacuum, like the absolute fastest speed that light can go, divided by the speed of light in the material, which makes sense, right? So that's the refractive index, n. So you're looking for sort of a ratio, really. So the slower the light is, the higher the refractive index is. Is that okay? If we imagine, this is just a simple dividing thing, right? So imagine on the top we've got the number of sweets, on the bottom we've got how many people there are, and n is how many sweets each person gets. Then if there were loads and loads and loads of people, if that number was really high, then you would get very few sweets each. And if there were hardly any people, you'd get loads of sweets each. So the slower light is, the higher the refractive index is. Yeah. The slower, the more it slows light down, the higher the refractive index. Here's a little example for you, just to kind of show you how it works before you go off onto the internet and find your own examples. So we've got this diagram here that we've looked at before. Hopefully this is all right. Yeah, nothing too scary about this. N equals sine I divided by sine R is another way to work out the refractive index of a substance. Now, what does that mean? You don't, obviously, a lot of you will know what sine means or be used to using sine in your calculator. You don't actually have to know what it means for this lesson. I don't love that. I would love to teach you what it means. I haven't really got time, and a lot of you know it already because it's kind of the math side of it. It's not the physics side of it. So for now, we're just going to say if you put sine into your calculator, you get the right answer. So the angle of incidence between the normal and the incident ray, we're going to call that I, yeah, for incidence. Physics has been kind to us for once. And we're going to call the angle of refraction R for refraction, all right? So if you did an experiment and you got a light box that could shine a sort of very pointed ray of light through air and into glass, and you did some measurements, then you might find, say, that the angle of incidence here is 50 degrees, and you got your protractor out and you said that the angle of refraction here was 31 degrees. What do? You just put that into your calculator, yeah? So the refractive index, how much glass is slowing this light down, would be sine I divided by sine R. So you just do on your calculator. Should we make it real? Yeah, here you go. Sine 50, close bracket, divided by sine 31, close bracket, equals 1.49. And because I prepared this question in advance, the refractive index of glass is, yes, about 1.5. So there you go. Please note, what are the units of refractive index? What are the units of refractive index? Is it meters, meters per second squared? Newtons. What are the units of refractive index? I'm pointing to the equation. What unit do you get if you divide sine I by sine R? Careful, careful. Let's go back a bit. What do you get if you divide a speed by a speed? Oh, it's tricky, isn't it? So we've talked about this before. It's always worth reiterating. When you do an equation, whatever you do to the number, you do to the units as well. So the refractive index, the number is the speed of light in a vacuum divided by the speed of light in material. And the unit for refractive index is whatever the unit for the speed of light is divided by whatever the unit for the speed of light is. Well, you know how like 1 divided by 1 is 1, and 3 divided by 3 is 1, and 100 divided by 100 is 1, and a quazillion divided by a quazillion is 1. So meters per second divided by meters per second is just sort of, it's just like, it's nothing. Meters divided by meters, you just cancel them out, okay? Is that all right? So refractive index of glass does not have a unit. It might test you on that if they were feeling dead tricksy. And then, yeah, I'm just going to give you, oops, sorry, that's my office. I'm going to give you a few GCSE questions, very simple past GCSE style questions. I'm not going to ask you to work out refractive index because some of you will want to practice that more at home. But I am going to show you one last very cool activity. I didn't ask you to do it because you might not have all the stuff and you might not want to get really messy, but if you've got the stuff, you should totally do it after this. I've got a Pyrex jug here and a glass. It would be better if the glass was Pyrex as well, but we'll say that hopefully these are fairly similar materials. I'm going to put the glass into the Pyrex jug. And what can you see? Well, you can see the glass inside the Pyrex jug, right? Okay. What's going to happen if I pour some vegetable oil into the jug? Some of you will have seen this before. You could think about why. Why is it happening? Let's have a go. I'm so pleased with this when I did this on Facebook yesterday, and you've got a much better view. Okay, so I'm going to fill, what shall I do first? I'll fill the glass inside the jug with some vegetable oil. There we go. So glass, very much on show. Loads of lovely bubbles. And now I'm going to pour some oil around it, like into the jug, but not into the glass. Oh, it's so good, isn't it? Can you see that? Can you see that the glass seems to completely disappear? Why is that happening? Little shout out to my husband who wanted to use the oil yesterday and I'd stolen it all. It's worth it though, isn't it? Why has that happened? Come on, if you've got loads of oil at home, if you're bulk buyers like we are, have a try. You can't, the glass has become invisible. What's going on? Perfectly visible from the top, not visible from down below. It's because the vegetable oil and glass have a very, very similar refractive index. So you see things when light travels from the object to your eyes. There's no bending of light going on, is there? It's just light is passing from, shouldn't lift it up. Light is passing from objects behind through the glass and through the olive oil without changing direction because it's sort of, the light is treating it as if it's just one big body of stuff. It's clever, isn't it? Super cool. Right. Have a go at these GCSE kind of past paper-ish questions that I wrote myself for copyright reasons. And then we'll call it a day. Let's squidge you up a bit. Okay, so your first question. A laser is shone at the surface of a swimming pool for physics reasons. Draw a line to show the path of the ray of light. And that's 2 marks for that. 2 marks. Be careful, don't make it too complicated. It might be so obvious that you think it's harder than it is. So you've got a kind of torch, a laser pointer, shining a ray of light at a swimming pool from an angle. So it starts from the top left and it shines towards the bottom right. The laser light is travelling through the air and it's hitting the surface of the water. What is going to happen? Draw a line to show the path of the ray of light. What is the name of that process? Question number 2, a ray of light passing into a glass block passes into a glass block as shown. So it's just going straight in at right angles, okay? You've got a glass block and you've got a ray of light coming from the top to the bottom of the screen, hitting the glass at a right angle. Describe what happens to the direction the light is travelling in. And finally, a ray of light refracts when leaving a piece of glass. So you've got a ray of light travelling through some glass, coming out into some air. What letter shows the angle of refraction? So there's an angle between the ray of light in the air and the glass block, which is A. B is the angle between the normal and the ray of light in the air. C is the angle between the ray of light in the glass block and the normal. And D is the angle between the ray of light in the glass block and the edge of the glass block. Whew. Which of those letters is the angle of refraction? While you're doing that, I'm going to attempt to pour vegetable oil back into a bottle. Is that a good idea? How are you doing? Should we go through it? Clearly I just need to do that every lesson, don't I? In order to stay quiet enough for you to answer the questions. Pouring from a jug of oil that has a glass of oil in it requires just enough concentration for me to not speak. Alright, number one. What's the 2 marks for? It's not for... You might have thought, oh, I'll just put an arrow on my ray of light. It's not, you don't really get a mark for showing an arrow. Well, one of the things you get a mark for is showing that the laser goes into the water. You got 1 mark for knowing, just bring it over here. You got 1 mark for knowing that because you might have thought that the surface of the water acted as a reflection and that the light would bounce straight off again. So you got a mark for just putting the light ray into the water, so well done if you did that. Now what I would do in an exam is draw the normal. Maybe I'd use a ruler in the exam, and then I'd go through it with my trusty pen. So I'm a ray of light, my pen is moving towards the water, the bottom of the pen where my hand is, that's hitting the water first, so that bit's going to slow down, isn't it, first. The top bit of the pen is still in the air, that's going to be moving faster. So we're going to get it pivoting like that. So it's going to move towards the normal. And that's what your 2 marks was for. Your 1 mark was just for it being in the water, and the other mark was for showing that it bent in the right direction, that it didn't go off like that, for example. Is that okay? What is the name of this process? Well, this was a much easier question at the end of the lesson that is called refraction. Once we've done diffraction as well, then that might get a little bit harder. But yeah, the name of the process was refraction. So you got 1 mark for showing it going into the water and 1 mark for it bending in the right direction. You get another mark for saying that is refraction happening, light bending because it's slowing down or speeding up. A ray of light passes into a glass block as shown. What happens? Well, there might have been a lot of students panicking because they thought that nothing happened, but they needed to say that something happened, so maybe they would have said, like, it slows down or something. No, nothing was the correct answer. Trust your instincts. Yeah, it doesn't change direction. Would have got you a mark. Well, yeah, describe what happens to the direction the light is travelling in. So nothing happens to the direction the light is travelling in or anything like that would have been totally fine. 3 was really tricky because nearly always with a diagram like this, the light is travelling from the air into the glass block, isn't it? That seems mean. Like, is that really testing your knowledge? Just testing how carefully you're reading the question. In this case, the incident ray is the one in the glass block. I guess maybe they were checking that you knew the incident ray was the sort of first ray and the refracted ray is the ray that has changed direction. So that's the incident ray inside the glass. That's the refracted ray. So the angle of refraction was the one between the refracted ray and the normal. So it was B. But if you said C, then that's probably good because they've tricked you and they won't trick you again if you ever actually do the exam. Phew. All right, you lot. You wonderful patient people. That is the end of my lesson on refraction. I'm going to very quickly, on my Facebook page, throw up a post. A totally useless post reminding everyone that the lesson, I guess, is here now to stay. But yeah, when you're watching live, a lot of you like to ask questions. In fact, someone has already messaged me to say, I have a question. How do I ask the question? So if you go to my Facebook page, Official Theatre of Science, on Facebook, then I'll put up a post now. What should I say? Any questions from my live IGCSE physics lesson today? Leave them here! Exclamation mark. Nice little colourful backgrounds. Oh yeah, look, mathsy. Okay. Little kiss. Because physics is intimidating. Got to put a kiss where you can. There we go. Right. Phew. Okay. So if you want to go over to YouTube now, to Facebook now, then at the very top of my page is a note saying, please leave any questions here. And if you've got a question, please do ask because your questions really make the lesson better. It's unbelievable. There's no way that I could do this job if people weren't watching. Absolutely no way. I couldn't be these people who just kind of stream like a pre-recorded lesson because the lesson would be terrible. My lessons are only anywhere near as good as they are because you keep going, oh, you got this wrong. Oh, I didn't understand that bit. And then I can tweak it and make it better. Okay, I'd better do my ad while I'm seeing if anyone's got a question. How it works is everything that I do is free. Everything that I do is free. Oh, also a bit of information, I suppose. Next week is our last week before half term. So we're doing a lesson next week. And then we've got a week off half term. And then when we come back, we'll be carrying on waves. And we'll do waves now until the summer holidays. Because it's only, what is it, like 6 or 7 weeks, I think, after half term. So in fact, we have 8 lessons left of waves. And then we'll start a whole new topic, energy, when we come back in September. Yeah, so if you want to support me, then it would be great if you would, because everything that I do is free and I just kind of rely on you to just support me anyway, and you are, so it's a job. It's totally amazing. Oh, someone's just liked this video. Thank you for reminding me to say please like and subscribe. I never say subscribe. It's subscribing, it's fun getting subscribers. But what's more important to me than subscribers is cash money. So the printouts for these lessons are free and available on my website. All the lessons that I've ever taught in IGCSE are stored on my website for watching on catch up. There is a homework PDF, which I've been very shoddy with this week because I've just been magazine packing, which is why I'm looking a little bit flustered and underslept, because it's magazine week. But anyway, that leads me nicely to why and how you can support me. If you go to my About section, then you will find a link to this website called Coffee. And people who want to support my lessons, which are completely free, sign up to support me on Coffee for £5 a month, or more if you like. A lot of people sign up with £6. Some people sign up with £9. You could sign up with £100 if you wanted to, but there's enough of you watching that you don't have to. And I'll send you Theatre of Science magazine. because I love writing it. Oh, I love writing. I love writing. I love researching stuff. I love Theatre Science Magazine. It's just a gorgeous hobby now that I have, and I post it out to my supporters, and it's the only thing they get that no one else who isn't paying me gets, if you know what I mean. It's like a kind of little present, I suppose. It takes me absolutely forever to write it. If you sign up with £5 a month, you get the one that is on mould. It's got a comic, and it's got it comes with a home compostable plastic bag, so you can grow some mould. It's got a choose your own adventure. No wonder it takes. You won't get that one. If you sign up with £6 a month, you get the sleep issue, which comes with some organic lavender. Oh, I've got some comments. And some fabric, so you can do some sewing. It's also got a choose your own adventure and a comic and an origami koala and lots of information about what happens to your brain when you're sleeping. But the latest issue has just come out. I'm super excited. How fast is light through a supernova? Oh, hello. Bastian wanted to show its diagram. Amazing. Why does nothing happen when it goes into... Okay, brilliant. Wow, these are some really good questions. Hello, Neve. Hello, Freya. Yeah, the brand new. So if you sign up to support me, you get this lovely welcome pack with some diffraction glasses, which will be very relevant in a week's time. And you get the past magazine or two, and then you're just on the list for when the new magazine comes out. But the new magazine, I took a year to write it. It's so big. There's so much. I mean, a lot of the work is like cutting it down and simplifying it. So you wouldn't think that I'd spent a year on this thing. But anyway, it's about spies, and it's out now, and I've said that the deadline has passed to get it. Actually, I'm going to pull it. I'm going to make it that new supporters can't have it. But the deadline was midnight last night if you're watching live. And obviously, I've taught 3 lessons today. So obviously, between midnight and now, I haven't packed up all the supporters that signed up last week and posted them off or last night. So if you really want it, if you've been thinking, oh yeah, I should support Laura, but I haven't got around to it, because you've got a brain like me, then if you sign up today, I'll still send you it. But don't tell the others, okay? Because I'm not going to do that for long. Because I like that my supporters are the ones that have Theatre Science Magazine, and that you can't just, like, the earlier you sign up, the more you get. All right. Okay, let's get to these questions. These are brilliant questions. How fast is light travelling through a supernova? So a supernova, the very last module that we'll do, we're doing 8 modules for this course. This is the 3rd module. When we get to, is it the very last one? It's astronomy. We will talk about what a supernova is. But basically a supernova is a star coming to the end of its life and collapsing, and then because of it's huge, right? So it's got a lot of gravity, so it collapses, and then because of the gravity and it coming together, it sort of gets squished and fires off in all directions. Well, it's just as fast as the speed of light, as far as I know. I mean, I haven't looked it up, but light doesn't travel faster than the speed of light. So, and it's in space where there are no particles. So I see what you mean, because you're thinking like that maybe it would kind of be extra accelerated, are you? Because it's kind of all exploding outwards. Yeah, I can see what you mean. But no, speed of light. It feels like a not very good answer to a very good question. Oh, Nina and Zoe, you're so welcome. Thank you for coming, loves. Bastian wanted to show his diagram. What is going on there? Why does nothing happen when it goes into the glass? From Tasha and Hannah. Why does not... Oh, you mean in the GCSE question? Like when it comes straight on? You mean like why doesn't anything happen? Why doesn't it change direction when it hits it straight on? Is that what you mean? Is that what you mean? So you could do this obviously like with your pen. If it's travelling straight forward, it doesn't change direction because it's all of the waves are hitting the glass like equally from kind of all angles. So no one bit of the wave speeds up or slows down. So that's why it travels straight through. We will learn more about that actually when we learn about lenses. I think that's our first lesson back after half term. Oh, I love that lesson where I get to take you into my downstairs toilet. It's more fun than it sounds. With a magnifying glass and a candle, and we look at what lenses can do. So we will learn a little bit more about that later. I hope that answers your question. Tasha and Hannah, hello. No, oh no, oh that's so embarrassing. Oh no, it's Tasha and Hannah's first live, and I made you sit around for 15 minutes with no explanation. I'm so sorry. Oh no. Your first time live, you always watch on catch up. Okay, so you do know me. You do know my brain. Still, even for me, that was very poor, wasn't it? God, can you imagine if I mean, I don't want to go back to classroom teaching, but I just couldn't now, could I? I couldn't. I would literally be fired. Oh, you're so welcome. I'm very happy to answer these questions. I'm loving these questions. Neve, would you consider doing geography? Oh, and IGCSE English? Do you mean IGCSE geography and IGCSE English? No, actually. I can almost categorically say no. I wouldn't want to do IGCSE English because I feel like you really need the training. I haven't had any training. Like with these GCSE questions, I have been the person marking like the mock exams for my classes, so I feel like I've got quite a good feeling for what's right and what's wrong and how you get the marks and how you lose marks. But essay writing, I haven't got a clue. I've never marked an essay, really. And I've never like been trained to teach people how to pass exams with essays. So I just feel like, I mean, I could, but there's so much that I'd want to do first. Geography is like a different kettle of fish. If I was going to do anything else, I'd do biology and chemistry. I mean, it'll be quite a long time because these lessons take ages to plan. But once I've got all the physics ones and I'm happy with those, it'd be nice to add some biology and chemistry, because then people can kind of pick and choose modules, and then they could do like double award if they wanted, or triple award. That would be cool. But yeah, I'll get through get through the physics first. This is its second time round, and yeah, I don't know. I watched my very first lesson back a couple of weeks ago and instantly spotted a mistake. It's like, this is so annoying. It's supposed to be perfect this second time round. All right. Anyway, is that everybody? Oh, thank you. Yes, that was the question. Oh, good. Excellent. Oh, well, it was very... Oh, Tasha and Hannah, I'm so pleased that you stuck around. Freya, last comment. Okay, I'm going to go. Thank you so much for joining me. So, yeah, next week, last lesson. I need to look it up again. I think it's on diffraction. And we'll talk about how refraction is different from diffraction. And then, yeah, we'll have a week off. I'll try and do it now, actually. I'll try and get that homework PDF updated so that you can have a go at like angles of refraction and reflection and that sort of thing. Okay, yeah, I'm going to go. I'll see you all very soon. Thank you so much for your... I rubbed it off the walls. Thank you so much for your support on my website that is called Coffee. I would love to send you a magazine or two. I'll